In this video, I'm going to show you how to protect an alcohol using a silyl ether. Now this reaction mechanism is very simple. We're just going to be using SN2 chemistry. Yet despite its simplicity, I have seen PhD chemists at major conferences show the mechanism for this reaction incorrectly. So let's just go over a few key points. Oxygen versus nitrogen. Which one is more electronegative? Just have to look at a periodic table to tell you that oxygen is more electronegative than nitrogen. Which one is a better nucleophile? Nitrogen is a better nucleophile. Okay, I need you to remember that electronegativity, right? The other word for that is greedy. That means that when oxygen has 2 bonds and 2 lone pairs, it is very greedy with those lone pairs. It doesn't want to use those electrons to make a bond. Remember what a nucleophile is. It's take these electrons and make a bond. Nitrogen has 2 electrons and it is less electronegativity. Nitrogen has 2 electrons and it is less electronegative. Therefore, it is less greedy. So it is more willing to do this. It's more willing to say, hey, I've got 2 electrons. I'm going to make a bond with you. Therefore, making it a better nucleophile. Okay, you got it? Looking at this question again. This is the reason why if you throw triethylamine into this system, you're going to get competition between the oxygen as a nucleophile and nitrogen as a nucleophile. The electrophile is the silicon with a good leaving group on it, right? Chlorine, great leaving group. Now, the problem is that the nitrogen is a better nucleophile. So what's going to happen first? Oxygen attacks silicon or nitrogen attacks silicon? The nitrogen is going to attack the silicon. So step 1 is the nitrogen attacks. And we end up with the nitrogen now positively charged. The chlorine got kicked off. It's negatively charged, hanging around. You get this sort of salt, okay? Now that's the first step. Why is this important? Well, in a paper by E.J. Corey, he showed that you can get this reaction to go without the use of triethylamine, but the yields are really low. Okay, so this can occur and you can work your way to the silyl ether, but you get really low yields. Think about why that would be. Well, 1, oxygen's not as good of a nucleophile. 2, the silicon is, you might say, well, gosh, that's a pretty sterically hindered atom. I need you to remember that silicon carbon bonds are longer than carbon-carbon bonds. So it's not as crowded as you would think, because those groups, the T-butyl group and the methyls and the chlorine, are held at a farther distance away. So they're actually not as cumbersome as if that was a carbon with a chlorine off of it. So don't worry too much at this point about the steric hindrance. But the problem is that the chlorine's a meh leaving group. It's a good leaving group, but given some of that steric hindrance, given the fact that oxygen is not a strong nucleophile, it's weaker, this is not a very efficient reaction. By having the nitrogen attack first and kick out the chlorine, you have now made an absolutely better leaving group. This is a way better leaving group than the chlorine. So you've also increased the steric hindrance, right? You got a lot more steric hindrance going on. So it really wants to leave. So you're kind of coaxing the alcohol now into activity. You're saying, hey, I kind of got myself in a pickle here. I really need help. I was okay before with this leaving group, but now I'm kind of screwed. I got a lot of steric hindrance going on, and the nitrogen just wants out, right? It wants to get back to its bond trend. So you've improved the leaving group ability, and you've, through steric hindrance, encouraged it. You've really enticed the oxygen to help out. Okay, the more reluctant nucleophile says, all right, I'll help you out. And here's the second SN2. So the first step, you're just installing a better leaving group. Using SN2 chemistry. And in the second step, you're actually just running the SN2 reaction. This gets you to your silyl ether, and you actually have triethylamine floating around. Guess what? Not only does it make it a better leaving group, but it also acts as a proton sponge. It helps neutralize things because, again, you've got chlorine minus floating around. You don't want to create a very acidic system. So this helps to buffer the medium. And now you have your silyl ether product, your protected alcohol.